Hello, everyone, and welcome to ML Done. And special welcome to Professor Belkin, and thank you so much for agreeing to being with us today. We're going to analyze a paper by Professor Belkin and his colleagues, which really questions, well, I would say sheds light onto the fact that why very rich models with millions and millions of parameters, like deep models, do not overfit and still have a strong and high level of generalizability. So that would be the main focus of our talk today. So Professor Belkin, welcome one more time. And let's just start with a general question. Could you just please introduce yourself briefly for us?
First, thank you, Mikhail. It's great to be here. So I am a professor at the New Religiolo Data Science Institute at the University of California, San Diego. And I do machine learning primarily.
Right. And could you tell us about your research interests? What were they and what are they now?
So I have worked on really all kinds of machine learning things, including clustering and semi-supervised learning and data derepresentation and, of course, supervised learning. And recently I have become extremely interested and obsessed, fascinated with neural networks. And what I've recently worked on was really trying to understand what is going on in neural network and trying to reconcile some sort of unexpected or puzzling aspect of this remarkable success of neural networks with our theoretical understanding. So that was sort of my primary research direction in the last, maybe 4 years or so.
So let's just get more towards the actual paper that we're here to talk about. So could you just, because you see this paper, as I was reading it, as I actually told you in our email, as I was reading the paper, I kept saying, whoa, oh my God, really? Oh my God. So these were the words in my head. So it really sheds light into the, the traditional U-shaped model capacity versus the generalizability of the model. And it just shows that that's not the whole picture. Could you tell us about the story behind this paper? Like, how did you start thinking about this and start questioning it and really dig deep into this?
Yeah, so the background in this is that it has, some years ago, it had become clear that something interesting was happening in neural networks. That what people observed is that you can train neural network to have very low empirical loss or empirical risks, so training on loss on the training set. And they just didn't seem to overfit very much. And this was very puzzling, not just to me. There was sort of a line of research trying to understand this. And if you actually dig a little bit deeper, this goes way back, and really, like you can see that even in the late 90s, there were some related questions. But I think recently there was this kind of more impetus to understand this, because neural networks really have become very, very prominent practically. So I was looking at this, and the way it actually happened, I gave a number of talks, and we had many discussions on why interpolating classifiers can be proved in some cases, or empirically observed, to give very good results. And by interpolating classifiers, I mean things which, or regression functions, things which fit the data, the training data exactly, have zero loss. And in fact, we wrote a paper with Daniel Su and Partha showing that some class of kernel methods can be proven to be optimal despite the fact that they fit the training data exactly. But then the questions we would get is like, okay, this is all great, but how does it relate to the classical bias variance trade-off, right? And there were many questions like that, and I always had to answer, well, I don't know, it looks different. And the same as neural network, right? Why do you, when you train neural network, you run your optimization process? Why is it any good? Why is the result good? And say, well, not clear. So then the kind of double descent curve specifically came from a little bit of serendipity or luck. My student, Sumik Mandal, was working on the question, what happens with random feature models, which is a random Fourier features, which is a class of models when you can choose a number of parameters. And you can, for example, choose a number of parameters to be much larger than the data, than the size of the data. And then what he observed empirically is that there was this remarkable pattern when we first did this U shape, and then after the U, it decreased again. And so that was very striking, but it took some time to actually, like, for a while, it was just a curiosity. And then at some point, it sort of clicked and it became clear that this is really the right pattern. And this is not just applicable to that specific model. So that was kind of the background for the story.
I'm going to put a link to the actual original paper in the description below. Also, I'm going to put a link to the summary of the paper at mldown.com. Now, when I was reading the paper, I was thinking those big models with millions of parameters, say deep models, they already have, I mean, whatever model have you, they already have some mechanisms to avoid overfitting, to prevent the model from overfitting. They have dropouts, they have regularization on the weights, on the parameters. Now, I wonder if those regularization methods were not applied in those models, would they still generalize well?
It's a slightly tricky question. Okay. The very simple one-word answer is yes. You would still see the same thing, but then I have to immediately clarify what I mean by saying yes. And I think there is something quite interesting is happening here. And this is actually one message of the paper, is that there is this clear separation between what we call classical regime and the modern regime. So in the classical regime, which is under-parametrized, the number of parameters is not enough to fit the data exactly. What's happening is that you are simply doing empirical minimization, right? You are choosing the model which fits the data best, and then hopefully you can prove something about it, or empirically it works well, or some other thing like that. In the modern, what we call modern regime, over-parametrized regime, there is more than one way to fit the data. So the way to think about, there is this whole manifold of predictors of hypotheses. In the hypothesis space, there is this whole manifold of predictors which fit the data exactly. Now, not all of them are good. And if you think about linear regression, it's kind of trivially true, right? Because you have this whole linear space of predictors. Some of them are going to be terrible. So how do you choose a predictor which is good? Well, you have to have this idea of an inductive bias, that you are somehow choosing something which you know for some reason should be good, or at least not too bad. It may not be optimal, but it's something that you think will be right. And the interesting thing that when you're training these models for neural networks or for linear models, the gradient descent itself, the method that you're using, has a sort of built-in inductive bias. And remarkably, that turns out to be quite good. So in a sense, maybe you don't need dropout and you don't need these other tricks, because somehow the procedure itself chooses a predictor which is, in a sense, good enough, at least reasonable.
Mm-hmm.
Now, if you want to get state of the art, you probably would benefit from the strict because it gives you, more knobs to really tune the things. And that's what often people do, right? They like adjust the parameters just so to get it like 1%.
Yeah.
But it's not necessary to just get good performance.
All right. Okay. That was very interesting. Could you just tell us about this idea of interpolation threshold and where it's so what is it and when does it usually happen? Is there a mathematical rule for it that for a given model people could say that definitively that around this point that is the ideal capacity, well, that is the capacity of the model that in which the thresholding, the interpolation threshold will happen?
Yeah, I really like interpolation threshold because it's kind of like, it's a very clear demarcation. So what it is, it's the capacity of the model. So imagine that I'm increasing model capacity by, for example, increasing the number of neurons in the neural network. And imagine that my data are fixed. Then at some point, I have enough capacity to fit the data exactly. And that is the interpolation threshold. That's essentially the number of parameters at which you can have zero loss. And the interesting thing is that this is a demarcation point between this classical world and the modern world. It's a signpost. You pass and you're in this different world. Like Alice in Wonderland, right? There is the world, and then you go down the rabbit hole. Things change.
But I don't know whether I read it in your paper or whether when I was doing some research, I got to a point where I think whatever the text was that I was reading, it was saying that the interpolation point has something to do with the number of instances in the data set or number of, I don't remember exactly what is there a relationship like that?
Yeah. So for that is the easiest way to think about it. Imagine I just have a regression problem or a binary classification problem. Then typically it's just the number of data points. So the number of parameters, and it's easy to see why this should be true, because think about it. Each parameter is a variable, right? You can change it. Each data point is a constraint because you want to fit it. So you want f of xi to be equal to yi. So when the number of parameters is equal to the number of constraints, that is a demarcation point. And for binary classification of a regression, is just when the number of data points is equal to the capacity of the model. So it's quite precise. And for this linear type of models, it's exactly that. You just see it.
And it's always after this particular point, as far as I understand, that if you continue increasing the capacity of the model, make it stronger and stronger, after this point, the test error or the test risk again will start descending for the second time, hence the double descent model, isn't it?
Exactly.
All right. Okay.
Exactly. And for many of these models, it's actually a very sharp peak. In fact, that's how we noticed it initially, because the peak was very obvious.
In the paper, you've said that the reason rich models have lower test risk than others is that the capacity of the model does not necessarily reflect how well the predictor matches the inductive bias appropriate for the problem at hand. This whole idea of inductive bias, what does it mean exactly, and how can we control this?
Yeah, so inductive bias, if it's kind of this, so in this setting, inductive bias is a question of what is our a priori belief about the data that we have. And in general, it is quite difficult to, you know, what, I don't know what the data is like, right? But you have this idea that certain aspects of the data are sort of should be in a certain way. So like smoothness is a good example of an inductive bias. Because what is smoothness? Smoothness, well, for a function, we say that it's smooth if its derivative, or maybe second derivative, is not too big, right? It doesn't change too much. How does it correspond to something that we have in machine learning? Well, imagine I have an image and I change 1 pixel of an image. Then the label of the image, well, it might change, but it's quite unlikely that it will change. So what we say is the label of the image is mostly constant, or the probability, say you have cats and dogs, right? The probability that this image is a cat, if you change 1 pixel, should only change very, very little. So that's a smoothness. That's saying that the probability doesn't change much with respect to the parameters. So the same, imagine I have some sensor and I'm moving the sensor from one location to another location, right? It can drop very drastically, but it's very rare, right? Usually you don't expect this. So that's this idea for smoothness. And we would like to have, because we have many predictors to fit the data, we would like to choose something which, for example, satisfies some constraint on the derivatives, that it's somehow smooth enough, that it's not like a checker. Imagine something which is not smooth, that's like a checkerboard, right? You move it by 1 pixel, changes. You move it another pixel, it changes again, kind of like chess. Chess is not a smooth game, right? You move a king from one square to another one, right? The position can change completely.
All of a sudden white was winning, and all of a sudden black is winning with just one move.
That's because you put your queen, you put your king on the check or something. You can take the queen. One thing is enough to break things completely.
Yeah, but you see, so in the paper, you've considered function smoothness as the appropriate inductive bias for the problems in the paper, for those specific data sets that you were dealing with. Now, it's a little bit hard for me to really understand this. How did you determine that this function smoothness is the appropriate inductive bias at explaining the problem at hand? And what if we have a different inductive bias, right? And if that is the case, then would you say that this double descent behavior will still happen?
Well, so first, how do we know that? So I would argue that this kind of smoothness is in fact a universal principle common to most problems, not all, but most problems that we have. So in a sense, and that's because of this idea of continuity, right? That when they change 1 pixel, I mean, think about evolution, for example. If a tiger from no tiger were just different by 1 pixel, right, we would never survive as a species, right? You have to have some sort of robust detection of the tiger. So there are some sort of physical evolutional reasons why, for most problems, you actually have this type of continuity. Now, it is still a rather vague kind of criterion, because when I say smoothness, I say, okay, the derivative is not very big, which is fine, but what the second derivative, third derivative, sum of the first 2 derivatives, right? It's not very specific. So I think it is not yet clear what kind of smoothness or what is exactly this inductive prior. What we know is that we can take some sort of inductive prior, which is kind of like 1 nearest neighbor, k nearest neighbor predictor. And then in most cases, that does an adequate job. But we probably need to understand much more what exactly is the notion of this bias. And this actually connects to something I worked much earlier on, this idea of manifold learning, that data in a low dimensional space, even though we perceive it as something like an image has many pixels. But the actual data sets, like imagine that I'm taking a picture of something rotating, right? The rotation has only a few degrees of freedom. But the image itself has thousands or millions of pixels. So that's an example of a low-dimensional manifold embedded in this high-dimensional space. In the prior, of course, needs to be adapted to this, but we're not yet at the point when we really understand completely.
All right. And would you say if we chose a different inductive bias? So, because as far as I understand, in the paper, you're saying that when you have rich models, that wild oscillation of the function goes away, because as if you have more knobs to control, you can search the hypothesis space much better for the ultimate, like the optimal set of weights, and you will choose simpler models, like the idea behind, I still don't know how to pronounce it, Occam's razor. Yes, simpler model is preferred. But now let's say another inductive bias, say nearest neighbor type, like data points in the same locality will have a similar output in the function. Now, which I assume it sort of implies smoothness again, because I mean, the output shouldn't change much, I suppose, for data points in the same neighborhood. But then again, if you go to maybe a little far away, I suppose it should change slowly, right? I mean, yeah. I think you still have smoothness as an underlying theme there. Maybe I'm just contradicting myself.
So maybe let me give you one example. Maybe so first, I think one nearest neighbor, k-nearest neighbor, is a very good example, right? Because it's basically saying that, well, things shouldn't change too much, right? Where if we find an example close to us, that's probably our best bet of what, you know, if I have an image of something, and I find that it's only different in 1 pixel from an image of a cat, it's a good bet it's a cat. Yeah. Right? Doesn't guarantee it, but it's a good bet. So that's one nearest neighbor kind of type of predictor. But let me give you an example of why different ideas of smoothness or different inductive biases can give you different results. So let's think about 2 types of neural networks. We can take a fully connected neural network, and we can take a convolutional neural network. Now you can run both on images, and they both give some results, which are non-trivial results, but we know that convolutional neural networks generally work significantly better on images than fully connected. So they both have some sort of inductive bias, and they both will exhibit double descent curve. But the performance of a convolutional neural network will be better because somehow the fact that there is this convolution and they aggregate it in a certain way is a much better fit for images themselves, because we know that, you know, like patches in images have some sort of, if you parallel transport one patch, somehow a face in one location of an image is the face is roughly equivalent to a face in another location of an image. While the fully connected neural network doesn't have this additional information, and it will generally perform worse. So that's the difference. So somehow they both have priors, they both exhibit double descent curve, but the inductive prior of a convolutional neural network is better tuned to the data, image data that we have, that we typically respond. Now, it is not true that this is always the case, right? Because imagine I take some completely different data, it may be that convolutional neural network will perform terribly, right? Fully connected will do much better.
I suppose with a convolutional neural network, whether it's 2D convolution or say 1D convolution, now correct me if I'm wrong, but I think that they imply that the inductive bias that the algorithm or the model is going to solve is that there is local dependencies between like adjacent values, like spatial dependency, right? Okay.
But this may not be true, right? For example, in many problems, these values, imagine I'm taking a document and I'm representing it as a bag of words, right? Then the ordering of this word, which are kind of like pixels, is completely arbitrary. There is
Yeah,
nothing.
yeah,
So taking some sort of window there and averaging of this window is a meaningless activity.
yeah. That's very true. Actually, that's very true. But you're saying that the double descent will still happen, even
Will
if
still happen.
okay, even if your inductive bias is not doesn't match the inductive bias of the actual problem. The performance will not be as good, but the behavior will still happen.
Exactly. The shape, so double descent is a description of the shape of the curve, right? It doesn't
Yeah.
say whether it's good or bad.
Mm-hmm.
And that is that whether it's good or bad is really the question of whether inductive bias fits the data.
Yeah. I get it now. Yeah, that was very interesting. Um, um, so okay, before I go to the oh, actually, I remember that as I was reading about this double descent behavior, at first I thought that okay, so as the model becomes more and more, well, parameterized, over-parametrized, the training error will keep going down and down and just hit zero and stay there. But after the interpolation point, you'll have the second descent and the test error. And after some time, you notice that the minimum, the minimum test error that you will achieve with an over-parameterized model could get lower than the minimum minimum test error that you had gotten, that you would have gotten had you stopped in the minimum of the traditional U-shape model before over-parameterizing model. And I thought that, okay, this second descent will always successfully get lower, will give us lower test error compared to the traditional U-shape model. And I remember that we talked about this, and I think I was wrong, right?
Yeah, so it's not always true that the bottom of the second, so but the second descent kind of, well, in most practical, it's not always true technically speaking, but in most practical examples it seems to just never go up again. It just keeps going down, but it's asymptotes. It doesn't go below some level. And the question, which is essentially like taking a very, very large model. And the question is, if this lower than the kind of the sweet spot, the bottom of the U, and it's unclear. So in sort of very simple experimental design, you can set it up depending on how exactly you set it up. It can go either way. In practice, it often seems that it is lower, but again, it is not consistent. It's not quite every time. And one question you may ask is that when it's lower, is it lower because it is really low, or is it lower because maybe in the classical regime, we cannot really find the best model because it's hard? So maybe one interesting thing here is that what it does, this modern regime allows us to find, because essentially we just take a very big model and we optimize it. So it makes finding something which is a very good model, makes finding it very easy. Now, is it better than the best model in the classical regime? Maybe it's not even so relevant in most situations, because if you cannot really find it, then what good is it, right? Mm-hmm. I mean, at least from a very sort of applied point of view, you don't even care. But from a theoretical point of view, of course, it's a really interesting question.
I see.
But so maybe the way to think about it gives us access to a lot of really good models. Mm-hmm. And it's a subtle question whether they're like really better than the truly best classical model. It depends.
I see. Okay. It's very interesting because in my head, when you increase the capacity of a model, it becomes a more complicated model. But at the same time, you're saying that because we have too many parameters, the solutions all of a sudden become, the functions all of a sudden become smoother, simpler, without mad oscillations. It's amazing how like for years and years, you think that you've understood the concept, and all of a sudden you read something, oh my God, no, I never got it actually in the first place. So the last question is this. Now, if we had not reached to, you know, this crazy amount of power, like computational power that nowadays we have with GPUs and, you know, monstrous servers, maybe we would have never thought about, okay, maybe this U-shape behavior, maybe it's not always like that. What, I wonder if I increase the capacity of the model, will something else happen or not? So I suppose because of having all these rich models and seeing the great performance, you questioned, like, why is this happening? Which is very interesting. Now I wonder, in your opinion, what other sort of well-founded theoretical stuff is out there that you think that, okay, for years and years they've been around, but there was a chance that we're not seeing the whole picture. There's a much bigger thing going on in the background.
Yeah, I think, yeah, that's a really, I think it's kind of it's really quite a wonderful fundamental question, right? I mean, one thing I would like to say is that I think there are two things which really happened recently. So as I mentioned, people have observed similar things, at least from the mid-90s. So there is a beautiful short note by Leo Breiman, famous statistician, who basically was asking these questions like in the 90s, why don't neural network overfit the data? And in fact, people observed similar things for boosting, and this whole development of theory of margins was motivated by trying to explain why boosting didn't seem to overfit. And I think so. Why now and why not in the 90s? I think there are really, like, one thing, as you mentioned, is that there is this big, you know, systems, and people really have been sort of much more practically have been just pushing them and getting these really good results, and sort of ignoring all the good theory that we had and basically said, no, like, your theory, we don't care. We just do stuff and it works better than anything you can do. It's a very fair point, I think.
Yeah.
I mean, it's good, right? If they can do something, it's without theory that we can do with theory, then we have to acknowledge that. So I think what happened is there was this sense of crisis. Is that there was a crisis of theory, and that really pushed me personally, for sure, but the whole community into looking into the things much more, you know, carefully. So I think the sense of crisis really helps, because then you have to kind of revisit what was the assumption that we didn't quite get right, or maybe got wrong, right? Now the question is, how do we know that there are no other things which we believe in and, you know, read in books and so on, that are not like that, and maybe they're like also at most, you know, half of the story or even less. And I think this is a really, really fundamental question, because if you think about, like, as scientists, we're kind of caught between these two. You know the story of Odysseus. There is, at some point, he has to navigate his ship between these two monsters, Scylla and Charybdis. And basically, you go a little bit to the left, you get one monster eats you, you go a little bit to the right, the other monster eats you. So how do you somehow make your way through that? And here we have two monsters. One is sort of believing sort of uncritically into this accepted wisdom. Another monster is not believing it acceptedly and going off the deep end. Right? If you believe in this accepted wisdom, you don't, you know, you don't see that this may be off. But if you don't believe it too much, it's also equally there. It may be even more dangerous in a sense, because accepted wisdom is usually right.
Mhm.
So I don't know that there is any sort of really, I mean, if I knew, of course, what something like that, of course, I would like write papers about this and give talks and so on. So
Yeah,
I don't know.
yeah.
So I don't think you like expected a
Yeah, yeah.
specific answer, right? But
Right,
I
right.
think it's something that we need to think about because there are certainly things like that, and they're always like that. They always exist, and we're probably like walking right on top of them without noticing. Like how do you notice something like that? So a crisis helps, but what else? Like how do you do it without this kind of acute crisis?
Yeah, yeah, that's true. I don't know. I have a feeling that the next big thing, I have a feeling that it will be in the realm of the interpretability of deep models. And I have a feeling that whenever it happens, I don't know, but I have a feeling that it will be directly connected to the development of quantum computers. I don't know, like that quantum behavior would give so much flexibility to the variables. And who knows, maybe the deep, complicated models that we have are just a very simplified version of capabilities that an actual brain has, that maybe through quantum computing or some other revolution, we will all of a sudden transform into that new type of network that, I mean, you've seen the quantum computers. You look at it, it looks like a kitchen appliance. I mean, it doesn't look like a computer at all.
I mean, one thing which I sort of have thought a little bit about at fairly superficial level, but is that I think from a biological point of view, it would make sense that a lot of biological systems are over-parametrized. Because it's a very easy and cheap way to do, because these are cheap update rules, right? Things like stochastic gradient descent. And if you think about it, what's the beauty of over-parametrization? You just have a bunch of parameters and you have this easy access to good models. So why wouldn't biology do something like that, right? You have some sort of little changes and many changes. Each one maybe just a little bit makes you just a little bit more adaptive. And maybe there's like some evolutionary processes can really be explained from that point of view. But I'm probably stepping sort of beyond my pay grade here.
Yeah, I mean, I've always thought that machine learning and what we do has always been mimicking nature. But again, you know, having talked about the smoothness of functions and finding simpler solutions to a problem with over-parameterized models, and yeah, I was just thinking things like DNA, right? A single change in a part of a DNA could result in a major change in the outcome. You know what I mean? Like I don't know whether I suppose I just thought about it now. I suppose that's not some sort of a linear, I not linear, but a smooth type of function. And if that's the case, because smoothness, as you said, seems like a universal type of you know, assumption underlying all the problems that we're dealing with machine learning. But right now, I just thought about this DNA thing. What do you think about that?
It's a good question. I don't know enough about this, but I would imagine that most changes in DNA probably don't do anything, right? It's only very specific changes which, you know, like, because we have a lot of mutations, right? Probably most of them are sort of irrelevant.
Yeah, that's a good.
Only
That's a
a
very
few
good
of them
point.
are really good or bad. So it's still, I think it's sort of roughly consistent with this idea of being mostly smooth.
I see. Yeah,
But
that's
once
actually
in
a
a
very good
while you
point.
hit on something. And plus, of course, well, if you look at something the scale of a human, right, we have like billions, trillions of cells, right? Each one of them is doing something. One cell is not going to make a huge difference.
Yeah, yeah,
It
yeah.
has to right? You have to activate some mechanism of replication. So this has to somehow replicate correctly and propagate to others.
Yeah, yeah, yeah. That's very true, actually. Yeah, well, I suppose, yeah, I think we went over all the questions that I had planned to ask you. And yeah, I really hope that you've enjoyed the interview, and thank you so much for being with us here at ML Done today. And thank you so much for your time.
Well, thank you, Mehran. That was great. Really enjoyed it. And yeah, thank you for inviting me.
You're most welcome. You're most welcome. So Professor Belkin, mind yourself, and I'm just gonna stop recording now.